there is a star. It is the closest star to our sun. It burns faintly in the southern sky, too dim to see with the naked eye, tucked behind the blinding glare of its larger companions in the Alpha Centauri system. Its name is Proxima Centauri, and it sits 4.24 light-years from Earth. That is the shortest stellar distance in the entire known cosmos, the nearest neighbour our solar system will ever have, and orbiting that star, completing one full circle every 11.2 Earth days, is a world, a rocky planet, roughly 1.27 times the mass of Earth, sitting squarely within the zone where liquid water could theoretically exist on its surface. Astronomers call it Proxima Centauri b. Most people simply call it Proxima b. It is, by every measure we possess, the closest potentially habitable planet to our own, the nearest place, beyond this thin blue sphere, where life as we know it might conceivably take root. Now here is the part that should trouble you. If we launched a spacecraft today using the most powerful rocket engine humanity has ever constructed, it would take more than 1,000 years to arrive. Not centuries in the poetic sense. Not a vague, hand-waving stretch of deep time. 1,000 years, 10 full centuries, more than 40 generations of human beings born, grown, aged, and buried in the dirt before that spacecraft so much as grazed the edges of the Proxima Centauri system. And that estimate is generous. Under most realistic propulsion scenarios, the journey would take far longer. 70,000 years, 100,000 years. Timescales so vast, they make the entire recorded history of human civilization look like a single startled breath. 4.24 light-years. It sounds so small. Light-years are supposed to be enormous, and this is barely 4 of them. The Milky Way galaxy stretches roughly 100,000 light-years across. The observable universe spans approximately 93 billion light-years from edge to edge. Against those numbers, 4.24 seems almost trivial. A short walk in cosmic terms, a hop across the street. But that intuition is a lie. It is a trick played on your mind by the comfortable abstraction of units you never experience. Because a light-year is not a casual measure of time. It is a measure of distance. 1 light-year is the distance that light itself, the fastest phenomenon in the known universe, covers in a single year of continuous travel. That is roughly 5.88 trillion miles, nearly 9.5 trillion kilometers. Multiply that by 4.24 and you arrive at the chasm between Earth and Proxima b. 25.2 trillion miles. A number so large it ceases to carry meaning in the human mind. A number that, when you truly grapple with it, begins to feel less like a distance and more like a verdict. We measure our lives in decades. We measure our civilizations in centuries. We measure our species in hundreds of thousands of years. And against the distance to the nearest habitable world, all of those timescales crumble into insignificance. We are not merely far from the stars. We are separated from them by a gulf that mocks our fastest machines, exhausts our most powerful fuels, and outlasts our most enduring institutions. Every generation of human beings has looked up at the night sky and believed, in some form, that the lights above were reachable, that someday, somehow, we would find a way, that the gap between wanting and arriving was merely a matter of time, of cleverness, of engineering. But the arithmetic of interstellar space does not care about belief. It does not bend for ambition. It simply is. Think about what 1,000 years means in human terms. 1,000 years ago, no one alive today had been born. No one alive then imagined the world we live in now. 1,000 years is 40 generations. It is the rise and fall of empires. It is the birth and death of entire languages. The Roman Empire, at its height, would have been a fading memory already centuries old. The printing press had not been invented. Gunpowder had not reached Europe. The very idea of science, as we understand it today, did not exist. And 1,000 years of travel, at the fastest speeds we can currently achieve, is still not enough to reach the nearest star that might harbour a world like ours. 1,000 years, and the spacecraft would still be drifting through the black, its destination still a faint point of light, barely distinguishable from the stars behind it. By the end of tonight, you are going to understand why that distance is not just large, but fundamentally, perhaps permanently, beyond the reach of anything humanity currently knows how to build. You are going to understand why 1,000 years is not a pessimistic estimate, but a startlingly optimistic one. You are going to understand the physics, the engineering, the energy requirements, and the brutal, unforgiving arithmetic that conspire to keep us stranded in our own solar neighborhood. And you are going to confront a question that most people never pause long enough to ask. A question that sits at the very heart of our species, our ambitions, and our future among the stars. What if the stars are simply too far away? Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let us begin. To understand why reaching Proxima b is so profoundly difficult, we first need to establish what we actually mean when we talk about cosmic distance. And to do that, we need to abandon every instinct our brains have developed over millions of years of evolution on the African plains. Human spatial reasoning was forged in a world of trees, rivers, scattered rock formations, and distant horizons. The farthest thing our ancestors ever needed to comprehend was the next mountain range, perhaps 50 or 60 miles away. Our brains are exquisitely calibrated for distances measured in footsteps. They collapse entirely, utterly, and without warning when confronted with the emptiness between stars. So let us build a ladder of scale, rung by rung, starting with the familiar and climbing toward the incomprehensible, the Earth. Our home planet has a circumference of approximately 24,900 miles at the equator. If you climbed into a car and drove at a steady 60 miles per hour, never stopping for fuel, food, or sleep, it would take you roughly 17 days to circle the globe. That is a distance most human beings can hold in their minds. It is large, certainly, but it is comprehensible. You can picture it, you can trace it on a map, you can feel the scale in your bones. Now let us step outward. The Moon, Earth's only natural satellite, orbits at an average distance of about 238,900 miles. At highway speed, that drive would take roughly 166 days, about 5.5 months of continuous driving. Farther, but still within the realm of human imagination. The Apollo astronauts made the trip in approximately 3 days using the Saturn V rocket, which produced 7.5 million pounds of thrust at liftoff. 3 days from launch pad to lunar orbit. It felt at the time like the beginning of an era. It felt like humanity was learning to walk among the stars. Next rung. The Sun sits approximately 93 million miles from Earth. This distance is so fundamental to astronomy that it has its own unit, the astronomical unit. At highway speed, 60 miles per hour, the drive from Earth to the Sun would take 177 years, longer than any human has ever lived. Already, at the scale of our own inner solar system, speed of car travel has become absurd. The numbers have outgrown the vehicle. But rockets are faster than cars, much faster. The Parker Solar Probe, launched by NASA in 2018, achieved a maximum speed of approximately 430,000 miles per hour during its closest passes to the Sun. That makes it the fastest human-made object in history. At that velocity, you could travel from Earth to the Sun in roughly 13 hours. The moon trip would take about 33 minutes. You could circle the Earth in about 3.5 minutes. Fast, staggeringly fast. The kind of speed that makes the solar system feel almost navigable. Here is your first scaled comparison. Imagine that the distance from Earth to the Sun, 93 million miles, were compressed down to the thickness of a single sheet of paper. One sheet. You can pick it up, fold it, slide it into your pocket. At that same scale, the distance from Earth to Proxima Centauri would be a stack of paper roughly 71 feet tall. From a single sheet to a 7-story building. That is the leap from interplanetary to interstellar. That is the chasm we are contemplating crossing. Now let us point our fastest spacecraft toward Proxima Centauri, the Parker Solar Probe, traveling at 430,000 miles per hour. The distance, 25.2 trillion miles. At that blistering speed, the journey would take approximately 6,700 years. Not 1,000, not 500, nearly 7 millennia. And that speed was only achieved because the probe was falling inward toward the Sun, exploiting the star's enormous gravitational well to accelerate. A spacecraft heading outward, away from the Sun, toward another star, fighting its way free of the solar system's gravity, would not have that luxury. It would need to generate its own speed, carry its own fuel, sustain its own momentum across a void so empty that a single hydrogen atom drifting through each cubic centimetre counts as relatively crowded space. Let us try another scaled comparison to anchor this distance differently. Imagine shrinking the Sun down to the size of a basketball. A standard basketball is about 9.4 inches in diameter. At that scale, the Earth would be a small peppercorn, roughly 2 millimeters across, sitting about 26 meters away from the basketball Sun. That is approximately 85 feet. You could stand at the Earth peppercorn and toss a ball to a friend standing at the basketball Sun. Jupiter, the largest planet in our solar system, would be about the size of a walnut, orbiting roughly 135 meters from the basketball. Neptune, the outermost major planet, would be a small marble floating 800 meters away, about half a mile. At this scale, you could walk from the Sun to Neptune in about 10 or 15 minutes at a comfortable pace. The entire solar system fits inside a small town. Now, where would Proxima Centauri be? At this same scale, with the Sun as a basketball sitting on your kitchen table, Proxima Centauri would be another ball, smaller, perhaps the size of a golf ball, resting approximately 6,900 kilometers away. That is the distance from London to New York City, roughly 4,300 miles. You have shrunk the Sun to something you can hold in one hand, compressed the entire solar system to a pleasant walk across a neighborhood, and the nearest star is still an entire ocean away. That is the scale of interstellar space. That is what 4.24 light-years actually means. The history of our species' awareness of this distance is itself a story of progressive humiliation. For most of human existence, the stars were assumed to be fairly close. The ancient Greeks placed them on a celestial sphere just beyond the orbit of Saturn, perhaps a few thousand Earth radii away. Aristotle believed the cosmos was finite and contained, a series of nested crystalline spheres carrying the planets and stars in perfect circles around a central, stationary Earth. This was not stupidity. It was a reasonable inference from the available evidence. The stars appeared fixed. They showed no parallax, no apparent shift in position as the seasons changed. If the Earth were truly moving, as some Greek philosophers like Aristarchus suggested, then the lack of stellar parallax meant either the Earth was stationary or the stars were unimaginably far away. Most chose the simpler explanation. It was not until the 16th century that Copernicus revived the heliocentric model, placing the Sun at the center and the Earth in motion around it. Kepler refined the orbits. Galileo pointed his telescopes skyward and saw evidence everywhere. And gradually, over the course of the 16th and 17th centuries, astronomers began to confront an uncomfortable implication. If the Earth truly orbits the Sun, covering roughly 186 million miles from one side of its orbit to the other over the course of 6 months, then the fact that the stars show virtually no parallax means they must be enormously far away, immensely, crushingly, incomprehensibly far. The first successful measurement of stellar parallax came in 1838. The German astronomer Friedrich Bessel, working at the Königsberg Observatory in Prussia, painstakingly measured the tiny angular shift of the star 61 Cygni against the more distant background stars as Earth moved from one side of its orbit to the other. The shift was minuscule, 0.314 arcseconds, less than 1/10,000th of a degree. From that vanishingly small angle, Bessel calculated the star's distance at roughly 10.3 light-years. For the first time in human history, the distance to a star had been measured, and that distance was terrifying. The stars were not thousands or millions of miles away. They were trillions upon trillions of miles away. The cosmos was not a cozy room with twinkling lights on the ceiling. It was a limitless abyss, dark and cold and empty, beyond anything the human mind had been designed to contemplate. Proxima Centauri itself was not identified until 1915, when the Scottish-born astronomer Robert Innes, working at the Union Observatory in Johannesburg, South Africa, noticed a faint red star that shared the same proper motion across the sky as the bright double star Alpha Centauri. Proper motion is the apparent drift of a star against the distant background, caused by the star's actual motion through the galaxy. When two stars share the same proper motion, it usually means they are gravitationally bound, traveling together through space. Further observations confirmed that this feeble red dwarf, invisible to the unaided eye despite being closer than any other star, was indeed a companion of the Alpha Centauri system. And careful distance measurements revealed something even more remarkable. This dim star was slightly closer to Earth than either of the two bright Alpha Centauri stars. It was the nearest star of all. It was named Proxima from the Latin word for nearest, a fitting name for an unfairly distant neighbour. The planet orbiting Proxima Centauri was not confirmed for another century. In 2016, a team led by Guillem Anglada Escudé at Queen Mary University of London, using decades of accumulated data from the European Southern Observatory's 3.6-metre telescope at La Silla, Chile, and from the HARP spectrograph, one of the most precise planet-hunting instruments ever built, announced the discovery of Proxima Centauri b. The detection was made using the radial velocity method. As the planet orbits its star, its gravitational pull causes the star to wobble ever so slightly. That wobble shifts the star's light toward the red end of the spectrum as it moves away, and toward the blue end as it moves closer. The speed of the wobble for Proxima Centauri was approximately 1.4 meters per second, a slow walking pace. The star was rocking gently, rhythmically, under the gravitational tug of an unseen companion. And from that barely detectable oscillation, astronomers deduced the existence of a world. Proxima b has a minimum mass of approximately 1.27 Earth masses. It orbits its host star once every 11.2 Earth days at a distance of about 7.5 million kilometers, which is roughly 5% of the Earth-Sun distance. For a star like our Sun, that would place the planet deep inside the scorching inner zone, far too hot for liquid water. But Proxima Centauri is not like our Sun. It is a red dwarf, a class M star, with a mass of about 12% the Sun's mass, and a luminosity of only 0.17% the Sun's luminosity. It is cool, it is dim, and at Proxima b's orbital distance, the planet receives approximately 65% of the radiant energy that Earth receives from the Sun. That is enough. It places Proxima b squarely within the habitable zone, the range of orbital distances where temperatures could, under the right atmospheric conditions, permit liquid water on the surface. Whether Proxima b actually possesses liquid water or an atmosphere or a magnetic field or any of the complex conditions necessary for life, as we understand it, remains entirely unknown. Red dwarf stars are notorious for violent behavior. They produce powerful stellar flares, sudden explosions of magnetic energy that release torrents of ultraviolet and X-ray radiation. Proxima Centauri is a known flare star. In March of 2018, astronomers using the Atacama Large Millimeter Array, known as ALMA, detected a superflare from Proxima Centauri that was roughly 10 times more energetic than the largest solar flares ever recorded from our Sun. If Proxima b lacks a strong global magnetic field to deflect charged particles and shield its surface, those flares could strip away its atmosphere over millions of years, leaving a bare, irradiated rock, a world in the habitable zone but not a habitable world. We do not know, we cannot know, not from here, not from 25.2 trillion miles away. Every measurement we make of Proxima b is indirect, inferred from wobbles in starlight, from transits and occultations that may or may not occur, depending on the alignment of the orbital plane. We have never seen this planet. We have never photographed it. We have only detected its gravitational fingerprint in the data. To truly understand what Proxima b is, whether it holds oceans or deserts, whether its skies are blue or burned away entirely, we would need to go there. Or at the very least, we would need to send something there. A probe, a camera, a sensor package capable of crossing the void and transmitting its findings back across 4.24 light-years of emptiness. Consider for a moment what it would mean to photograph Proxima b directly. The planet orbits its star at a distance of 7.5 million kilometers, which at 4.24 light-years from Earth translates to an angular separation of approximately 0.037 arcseconds. That is unimaginably tiny. To resolve the planet as a single pixel of light, separate from the glare of its host star, would require a telescope with an effective diameter of roughly 100 meters operating at visible wavelengths. For comparison, The James Webb Space Telescope, the most powerful space telescope ever launched, has a primary mirror 6.5 meters in diameter. We would need a mirror more than 15 times larger, operating in space, equipped with a coronagraph capable of suppressing the starlight of Proxima Centauri by a factor of roughly 10 billion to reveal the planet lurking beside it. Such an instrument is not on any space agency's drawing board. It is a technology of the mid to late 21st century at the earliest. And even if we built it, we would see Proxima b as a single pale dot, a pixel, a point of light whose spectrum might tell us about the composition of the planet's atmosphere, but nothing about its surface, its geography, its weather, its oceans, its life. To learn what Proxima b truly is, we need to be there, and we cannot be there. Not yet, perhaps not for a very long time. And this is where the problem begins to reveal itself in its full, unforgiving dimensions. Because the distance between here and there is not merely large, it is a barrier of a fundamentally different character than any obstacle humanity has previously confronted. It is not a mountain to be climbed, or an ocean to be crossed, or a frontier to be settled. It is a gap in the fabric of physical accessibility itself. The laws of physics do not explicitly forbid the journey, but they impose costs so vast, so far beyond our present capabilities, that the word impossible begins to feel less like an exaggeration and more like a factual description of the situation. Let us construct one more comparison before we move deeper. The speed of Voyager 1, the fastest spacecraft ever to leave the vicinity of our solar system, launched in 1977, Voyager 1 received gravitational assists from Jupiter and Saturn that boosted its velocity to approximately 38,000 miles per hour, about 17 kilometers per second relative to the Sun. It is now more than 15 billion miles from Earth, having crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in August of 2012. At its current speed, Voyager 1 covers roughly 3.6 astronomical units per year. That sounds fast. It is fast for a human-built machine, but Proxima Centauri is approximately 268,000 astronomical units away. At Voyager 1's speed, the journey would take about 73,000 years. To appreciate that number, consider this. 73,000 years ago, Homo sapiens was a young species, barely beginning its migration out of Africa. Neanderthals still walked the Earth. The last ice age had not yet reached its peak. Agriculture would not be invented for another 60,000 years. Written language would not appear for another 68,000 years. Every civilization, every empire, every invention, every war, every discovery, every poem, every song in human history, all of it fits inside a window of time shorter than the flight time of Voyager 1 to the nearest star. The universe, it seems, was not designed with travelers in mind. Here is one final exercise in scale before we leave this section. Consider time as a measure of distance. Light travels at approximately 299,792 kilometers per second. That is roughly 186,000 miles per second. In 1 second, a beam of light can circle the Earth 7.5 times. In 1 minute, light travels about 11.2 million miles. In 8 minutes and 20 seconds, light crosses the distance from the Sun to the Earth. In about 5.5 hours, light reaches Pluto. In roughly 4 hours and 15 minutes, it reaches Neptune. Our entire solar system, from the Sun to the orbit of Neptune, is roughly a light day across, depending on how generously you define the boundary. But the distance to Proxima Centauri is 4.24 years, not light seconds, not light minutes, not light hours, light years. If you sent a radio signal from Earth right now, a message encoded in electromagnetic waves, traveling at the universal speed limit, the fastest speed at which any information can propagate through the vacuum of space, that signal would not arrive at Proxima Centauri for 4 years and about 3 months. And if someone or something were there to receive it and immediately transmit a response, the reply would not reach Earth for another 4 years and 3 months. A single exchange of messages, a single question and answer, would span nearly a decade. This is not communication, it is correspondence across an abyss. It is a conversation conducted at the pace of geological eras, compressed into the span of a career. And this gap, This 4.24 light-year gap is the smallest interstellar distance in the sky. The next nearest star system, Wolf 359, lies about 7.9 light-years away. Barnard's star is about 6 light-years distant. Sirius, the brightest star visible from Earth, is 8.6 light-years away. The vast majority of stars in the Milky Way are hundreds, thousands, or tens of thousands of light-years from our Sun. The galactic center lies roughly 26,000 light-years away. If we cannot cross 4.24 light-years, we cannot cross any of them. If Proxima b is unreachable, then every star in the galaxy is unreachable. The nearest neighbor is the test case for all the others. And we are failing the test. Let us pause for a moment and consider what this means for the way we think about the cosmos. When we look at photographs from the Hubble Space Telescope or the James Webb Space Telescope, we see galaxies scattered across the void, like grains of sand on a dark beach. Each grain contains billions of stars. Each star may host planets. The universe appears impossibly rich, impossibly full, impossibly inviting. But the fullness is an illusion of perspective. We see the universe compressed onto a flat image, distances collapsed into angles, light years folded into pixels. In reality, those galaxies are separated by millions of light years of emptiness. The space between them is not merely empty, it is expanding, stretching, growing larger with every passing second. The universe is not a garden of stars. It is an ocean of void, with rare, isolated islands of matter drifting ever further apart. If you drove a car from Earth to Proxima Centauri at 60 miles per hour, without stopping, the trip would take 47 million years. Let that image form in your mind. 47 million years of highway. 47 million years of white lines and asphalt stretching to the vanishing point. If you had started driving at the time the dinosaurs were wiped out by the Chicxulub asteroid 66 million years ago, you would still not have arrived. You would have roughly 19 million years of driving still ahead of you. The absurdity of this image is its purpose. It forces the mind to confront the gulf between human experience and cosmic reality. We evolved to navigate landscapes measured in miles. The universe operates in light years. The conversion between the two is not merely large, it is violent. It breaks the intuitive framework entirely. Here is one more comparison before we turn to the physics. Imagine the entire 4.24 light-year distance from Earth to Proxima Centauri compressed to the length of a football field, 100 yards. At that scale, how far would the Voyager 1 spacecraft, the fastest object humans have ever sent into interstellar space, have travelled in its nearly 50 years of flight? The answer is approximately 1/5 of an inch, less than the width of a pencil lead. 50 years of travel at 38,000 miles per hour, and on a football field that represents the distance to the nearest star, Voyager has moved a fraction of an inch. That is the scale of the problem. That is what 4.24 light-years means when stripped of its abstraction and laid bare against the reality of our machines. The core problem is energy, not politics, not funding, not the difficulty of building complex machines, though all of those are real and formidable obstacles. The fundamental barrier between Earth and Proxima b is the sheer, staggering amount of energy required to accelerate any meaningful mass to any meaningful fraction of the speed of light. And then, if you want to do anything useful when you arrive, to decelerate that mass back down again. This is not a problem of ambition or willpower. It is not a problem that more money or more political commitment can solve in isolation. It is a problem of physics. It is baked into the architecture of the universe. And physics does not negotiate. Physics does not care about deadlines. Physics does not respond to funding cycles, or national pride, or the desperate yearning of a curious species to know what lies beyond. Let us build the argument carefully, because the implications are enormous. To travel from one point to another in space, you must change your velocity. This is the most basic requirement of spaceflight. In the vacuum of space, there is no friction, no air resistance, no road beneath your wheels to push against. The only way to change your velocity is to expel mass in the opposite direction. You carry propellant. You heat it, ignite it, or accelerate it, and you throw it out the back of your vehicle at high speed. The reaction, Newton's third law in its purest expression, pushes you forward. Every rocket ever built, from Robert Goddard's first liquid-fueled rocket in 1926 to the Saturn V, that carried Apollo astronauts to the Moon to the Falcon Heavy, that lifts payloads into orbit today, operates on this single principle: action and reaction, mass thrown backward, vehicle pushed forward. The relationship between how much propellant you carry, how fast you expel it, and how much velocity change you achieve is described by the Tsiolkovsky rocket equation. This equation was first derived by the Russian schoolteacher and visionary Konstantin Tsiolkovsky in 1897, decades before the first practical rocket was built. The equation is simple in its form and devastating in its implications. It states that the change in velocity of a rocket, commonly called delta V in aerospace engineering, is equal to the exhaust velocity of the propellant multiplied by the natural logarithm of the ratio of the rocket's initial mass to its final mass. The initial mass includes everything: payload, structure, engines, and fuel. The final mass is everything minus the fuel, the dry mass that remains after all the propellant has been expended. The critical word in that description is logarithm. The relationship between fuel and velocity is logarithmic. This means that as you demand higher and higher velocities, the amount of fuel required does not grow linearly. It grows exponentially. If you want to double your delta V, you do not merely double your fuel. You square your mass ratio, or cube it, or raise it to higher and higher powers, depending on the exhaust velocity of your engine. Small increases in desired speed translate to enormous increases in required fuel mass. This is the tyranny of the rocket equation, a phrase coined by astronautics pioneer Donald Pettit, and it governs every attempt to reach the stars. For chemical rockets, the workhorses of our current space age, the exhaust velocity is typically between 3 and 4.5 kilometers per second. The Space Shuttle's main engines achieved an exhaust velocity of about 4.4 kilometers per second. The most efficient chemical rocket engines ever tested reach perhaps 4.5. This is a hard physical limit. Chemical energy, the energy stored in molecular bonds and released when those bonds break, can only accelerate exhaust gases so fast. No chemical reaction can produce exhaust velocities significantly higher than about 5 kilometers per second. The energy density is simply too low. Now consider the velocity needed to reach Proxima b. To cover 4.24 light-years within 1,000 years, a spacecraft would need to sustain an average velocity of approximately 4,600 kilometers per second. That is roughly 1.5% of the speed of light. 1.5% sounds modest. It sounds almost lazy. But in absolute terms, it is a velocity of over 10 million miles per hour. And to reach it using a chemical rocket with an exhaust velocity of 4.5 kilometers per second, the Tsiolkovsky equation demands a mass ratio that transcends absurdity. The number has more digits than there are atoms in the observable universe. You would need more propellant than exists in the known cosmos. Chemical rockets cannot reach the stars. They cannot come within 1 million miles of reaching the stars. They are the wrong tool, by a factor so enormous that the comparison itself becomes meaningless. This is why no serious scientist, no credible engineer, has ever proposed a chemical rocket for an interstellar mission. The energy density of chemical bonds is simply too feeble. The exhaust velocity is too slow. The mass ratio spirals into mathematical infinity long before you achieve any useful fraction of light speed. If humanity ever crosses the interstellar gulf, it will not be with chemical propulsion. That much is certain. That much has been certain since Tsiolkovsky first wrote his equation on a chalkboard in Imperial Russia more than a century ago. To appreciate just how profound this limitation is, consider a concrete example. The Saturn V, the rocket that carried Apollo astronauts to the Moon, was one of the most powerful machines ever built. It stood 363 feet tall, weighed approximately 6.5 million pounds fully fueled, and produced 7.5 million pounds of thrust at liftoff. It consumed roughly 20 tons of fuel per second during its first stage burn, and after expending all of that fuel, all of that mass, all of that engineering brilliance, it accelerated its payload to a velocity of roughly 25,000 miles per hour, fast enough to escape Earth's gravity, fast enough to reach the Moon in 3 days, and approximately 0.004% of the speed of light. If you strapped a Saturn V to a payload and pointed it at Proxima Centauri, assuming you could somehow refuel it continuously, you would need to burn that rocket for roughly 400,000 years to reach the nearest star, and you would need a fuel supply weighing more than the Sun. This illustrates a point that cannot be overstated. The gap between planetary travel and interstellar travel is not a difference of degree. It is a difference of kind. It is the difference between wading across a stream and swimming across the Pacific Ocean. The tools that work for one are useless for the other. The muscles that carry you across the stream will not carry you across the Pacific. Something fundamentally different is required. So we look upward on the energy ladder. The next rung is nuclear energy. Nuclear fission, the splitting of heavy atomic nuclei like uranium-235 or plutonium-239, releases roughly 1 million times more energy per kilogram of fuel than chemical combustion. This is not a marginal improvement. It is a leap of 6 orders of magnitude. A single kilogram of uranium, fully fissioned, releases approximately 82 terajoules of energy, equivalent to burning roughly 2,000 tons of coal. Nuclear energy was the foundation of the first serious interstellar mission concepts, and it remains central to many proposals today. The difference between chemical and nuclear energy densities cannot be overstated. Consider a simple comparison. 1 kilogram of liquid hydrogen and liquid oxygen burned together in a chemical rocket engine releases approximately 13.6 megajoules of energy. 1 kilogram of uranium-235, fully fissioned, releases approximately 82.1 million megajoules. That is roughly 6 million times more energy per unit mass. If you could harness nuclear fission with perfect efficiency, the fuel requirements for any given mission would shrink by a factor of millions compared to chemical propulsion. This is why nuclear energy seemed, in the early days of the space age, like the obvious key to interstellar travel. The energy was there, locked inside the atomic nucleus, waiting to be released. But the devil, as always, lives in the details. Project Orion, which we will examine more fully in the next section, proposed using nuclear explosions for propulsion. But even setting aside the specific engineering of Orion, the fundamental numbers for fission-powered rocketry are sobering. A well-designed nuclear thermal rocket, one that uses a fission reactor to heat a propellant like hydrogen to extreme temperatures and expel it at high velocity, can achieve exhaust velocities of roughly 8 to 9 kilometers per second. Better than chemical, twice as good, roughly, but still woefully inadequate for interstellar distances. At 9 kilometers per second exhaust velocity, reaching 1.5% of the speed of light requires a mass ratio of approximately e to the power of 500. That is a number so large that writing it out would fill pages. The fuel mass required dwarfs the mass of the Earth itself. Nuclear thermal rockets, like chemical rockets, are solar system technology. They can open up Mars, the asteroid belt, the moons of Jupiter, but they cannot reach the stars. What about nuclear fusion? Fusion, the merging of light nuclei, the process that powers the Sun and every star in the visible universe, releases even more energy per unit mass than fission. The deuterium-tritium reaction, the easiest fusion reaction to initiate, converts approximately 0.37% of the fuel mass directly into energy. That fraction sounds tiny, but when multiplied by the speed of light squared, it translates to immense energy release. The theoretical exhaust velocity for a fusion-powered rocket engine, depending on design, could reach 10,000 to 12,000 kilometers per second, perhaps even higher in some optimistic configurations. 3 to 4% of the speed of light straight from the exhaust nozzle. This starts to feel promising. At an exhaust velocity of 12,000 kilometers per second, reaching 10% of light speed requires a mass ratio of about 2.3. That means for every kilogram of payload, you need about 1.3 kilograms of fuel. That is almost manageable. That is the kind of mass ratio that aerospace engineers know how to work with. For a moment, the arithmetic appears to relent. The exponential curve of the rocket equation finally seems to flatten. The stars seem, briefly, almost within reach. But here's the problem. We do not have fusion engines. We do not even have controlled fusion power generation. The International Thermonuclear Experimental Reactor, ITER, under construction in Cadarache, in southern France, is designed to demonstrate that sustained fusion energy production is physically possible. It is one of the most ambitious and expensive scientific projects in human history, with a projected total cost exceeding $22 billion and a construction timeline that has stretched across decades of delays. ITER is a tokamak, a massive donut-shaped device that uses superconducting magnets to confine a plasma of hydrogen isotopes at temperatures exceeding 150 million degrees Celsius, roughly 10 times hotter than the core of the Sun. The entire machine weighs approximately 23,000 tons. It fills a building the size of a cathedral, and ITER is not an engine, it is an experiment. It is designed to sit on the ground, connected to the power grid, surrounded by cooling systems and support infrastructure, and produce a brief pulse of fusion power, lasting perhaps 400 to 600 seconds. The idea of miniaturizing this technology, of making it compact enough to fit on a spacecraft, light enough to fly, reliable enough to operate for decades or centuries without maintenance or human intervention, and powerful enough to accelerate a meaningful payload to a significant fraction of light speed, is not a near-term engineering challenge. It is a challenge that may take centuries to solve, if it can be solved at all in the form that current tokamak designs suggest. Other fusion approaches exist: inertial confinement, magnetic mirrors, field-reversed configurations, but none has yet demonstrated net energy gain, let alone a flight-ready engine. And it gets worse. Even if you solve the engine, you face the deceleration problem. A spacecraft that accelerates to 10% of the speed of light must, if it wishes to enter orbit around Proxima Centauri or conduct any meaningful science at the destination, slow down again. Deceleration requires just as much energy as acceleration. The fuel for deceleration must be carried from the very beginning of the journey, which means that fuel adds to the mass that must be accelerated, which means you need more fuel for the acceleration phase, which demands still more deceleration fuel. This is the rocket equation compounding upon itself, a vicious exponential spiral that engineers call the mass ratio problem. For a mission that must both accelerate and decelerate, the mass ratio is not doubled, it is squared. A mission with a mass ratio of 2.3 for acceleration alone becomes a mission with a mass ratio of 5.3 for a full accelerate-decelerate profile. That means more than 4 kilograms of fuel for every kilogram of payload. Still feasible in theory for a fusion rocket, but the total fuel mass for a crewed mission with a habitat weighing thousands of tons becomes staggering. Tens of thousands of tons of fusion fuel, perhaps hundreds of thousands. And the deceleration problem has its own cruel subtlety. If you are decelerating into a star system, you are approaching that star system bow first, with your engine pointing forward and your exhaust blasting ahead of you. That exhaust, a stream of superheated plasma at thousands of kilometers per second, would announce your arrival to anyone or anything in the target system with the subtlety of a searchlight. More practically, the exhaust would need to be directed with extraordinary precision to avoid destabilizing the ship's trajectory. Any asymmetry in the thrust, any imbalance in the deceleration burn, and the ship veers off course into the interstellar void, unable to correct because it has already expended most of its fuel. Deceleration is not just an energy problem, it is a control problem, a navigation problem, and a structural problem, all operating at velocities where the margin for error is effectively zero. There is a conceptual workaround sometimes discussed in the literature: magnetic braking. If Proxima Centauri has a stellar wind, a stream of charged particles flowing outward from the star, then a spacecraft equipped with a large magnetic sail could potentially slow down by pushing against that wind as it approaches. The idea is elegant. Use the target star's own energy output to decelerate the spacecraft, eliminating the need to carry deceleration fuel. But magnetic braking imposes its own demands. The magnetic sail would need to be enormous, perhaps hundreds of kilometers in diameter, to generate enough drag against the tenuous stellar wind at interstellar approach distances. And it would only work at relatively low speeds. At 10% of light speed, the kinetic energy of the spacecraft is so enormous that no stellar wind, however energetic, could arrest it in time. Magnetic braking might slow a ship from 1% of light speed to orbital velocity. It cannot slow a ship from 10%. Then there is antimatter, the theoretical ultimate fuel. When a particle of matter collides with its antiparticle, they annihilate each other completely, converting 100% of their combined mass into energy in the form of high-energy gamma rays. 1 kilogram of antimatter reacting with 1 kilogram of matter releases approximately 180 petajoules of energy. That is equivalent to roughly 43 megatons of TNT, more energy than the annual electrical output of many nations. Antimatter propulsion could theoretically achieve exhaust velocities approaching the speed of light itself, effectively neutralizing the tyranny of the rocket equation. But antimatter exists, for practical purposes, in quantities so small that the word scarce becomes a grotesque understatement. The total amount of antimatter produced by all the particle accelerators on Earth over the entire history of particle physics amounts to less than 20 nanograms, 20 billionths of a gram. This is not a fuel reserve, it is a laboratory curiosity. At current production costs and efficiencies, manufacturing a single gram of antimatter would require approximately $62.5 trillion and more energy than the entire global economy consumes in a year. To fuel even a modest interstellar mission would require kilograms of antimatter. The cost would exceed the gross domestic product of the planet by orders of magnitude. Storage compounds the impossibility. Antimatter annihilates instantly on contact with any normal matter. It cannot touch the walls of its container. It must be levitated in a perfect vacuum using magnetic fields, a technology called a penning trap. Current experiments have stored small numbers of antihydrogen atoms for periods of up to about 1,000 seconds, scaling from individual atoms to grams, while maintaining containment through the vibrations, accelerations, and thermal extremes of a multi-decade space mission. Represents a leap in technology so vast that no responsible timeline can be assigned to it. It is not a problem for the next generation. It may not be a problem for the next 10 generations. There is also a subtlety about antimatter that is easy to overlook, even if you could produce and store it. The annihilation products are not easy to use for propulsion. When a proton and an antiproton annihilate, the primary products are pions, unstable subatomic particles that decay rapidly into muons and then into electrons, positrons, neutrinos, and gamma rays. The gamma rays carry a significant fraction of the annihilation energy, but gamma rays are extraordinarily difficult to direct or reflect. They pass through most materials. You cannot bounce them off a nozzle wall the way you bounce hot gas in a conventional rocket. Capturing and directing gamma-ray energy into useful thrust requires technologies that do not exist and may require exotic material properties that physics does not permit. Some antimatter engine designs propose using the charged pions and muons directly, guiding them with magnetic fields to produce thrust, but the efficiency of this conversion is limited, and the engineering is fiercely difficult. So here stands the energy crisis in full. Chemical propulsion fails by a factor of infinity. Nuclear fission fails by a factor of billions. Fusion propulsion works in theory, but does not exist in practice. Antimatter propulsion works in theory, but cannot be produced or stored in meaningful quantities. Each step up the energy ladder brings us closer to a theoretically viable interstellar engine, and each step reveals new barriers that are, in their own way, as impassable as the ones they replace. But here is what makes this truly terrifying. The rocket equation is not an engineering limitation. It is not a manufacturing challenge. It is not a funding gap. It is a law of nature. It is as fundamental to the physics of motion as gravity or electromagnetism. No amount of clever engineering can violate it. No breakthrough material or revolutionary design can circumvent it. You can change the exhaust velocity. You can change the fuel. But you cannot change the equation. And that equation says, with mathematical certainty, that accelerating mass across interstellar distances requires energies of a scale that current human civilization cannot produce, cannot store, and cannot control. We are not waiting for a better engine. We are staring at a boundary in the structure of physics itself. There is yet another dimension to this problem, one that is seldom discussed but deeply important. Propulsion is not the only physical challenge of interstellar travel. Even if you solve the engine, even if you find the energy, you must contend with the interstellar medium itself. Space between the stars is not perfectly empty. It contains a thin haze of gas, mostly hydrogen, at a density of roughly 1 atom per cubic centimeter, along with tiny particles of interstellar dust, grains of carbon, silicate, and ice, each measuring a fraction of a micrometer across. At ordinary speeds, this material is harmless. At 10% of the speed of light, it becomes deadly. A grain of dust weighing 1/1,000,000th of a gram, encountered at 10% of the speed of light, strikes with the energy of a small bomb. At 30,000 kilometers per second, the kinetic energy of even a microgram of matter is approximately 4.5 times 10 to the 8 joules. That is comparable to the energy released by 100 kilograms of TNT. A spacecraft traveling at interstellar velocities would encounter millions of such particles over the course of a 4-light-year journey. Each impact would erode the hull, damage instruments, and degrade the ship's structural integrity. Over decades of travel, the cumulative effect could be catastrophic. Shielding against interstellar dust at these velocities is an unsolved problem. The shield itself would need to absorb enormous energies without being destroyed, adding mass to the spacecraft, which in turn demands more fuel, which spirals back into the rocket equation. There is also the problem of cosmic radiation. Outside the protective bubble of our sun's magnetic field, the heliosphere, a spacecraft is exposed to the full flux of galactic cosmic rays, high-energy protons and heavier nuclei accelerated by supernovae and other violent astrophysical events to speeds approaching the speed of light. These particles penetrate deep into matter, damaging electronics, degrading materials, and posing severe health risks to any biological passengers. Over a journey of decades or centuries, cumulative radiation damage could render onboard electronics inoperative and expose human occupants to lethal doses. Shielding against cosmic rays requires mass, typically water or other hydrogen-rich materials, and that mass must be accelerated alongside everything else. Then there is the problem of communication. A spacecraft at Proxima Centauri would be 4.24 light-years from Earth. Any signal it transmits, no matter how powerful, would take 4.24 years to reach us, and signals weaken with distance, according to the inverse square law. A radio transmitter that produces a strong signal at 1,000,000 kilometers produces a signal 1 trillion times weaker at 1 billion kilometers. At the distance of Proxima Centauri, even the most powerful transmitters conceivable would deliver only the faintest whisper to Earth-based receivers. Receiving data from an interstellar probe would require antenna arrays of extraordinary size and sensitivity, maintained and operated for decades while waiting for a signal that might arrive as little more than a few photons per second. Each of these challenges, dust erosion, cosmic radiation, communications, compounds the propulsion problem. Each adds mass, complexity, and risk. Each demands technologies that do not yet exist, and each must be solved simultaneously, because a mission that solves propulsion but fails at communications, or solves communications but fails at radiation shielding, is a mission that fails entirely. The interstellar problem is not a single problem. It is a constellation of problems, each reinforcing the others, each adding layers of difficulty to an endeavor already at the edge of physical possibility. There is also the question of heat. A spacecraft accelerating at any meaningful rate generates heat. The engine produces heat. The reactor produces heat. Even the slow friction of the interstellar medium against the ship's hull at high velocity produces heat. And in the vacuum of space, there is only one way to dissipate heat: radiation. Heat must be radiated away from the spacecraft's surface in the form of infrared photons. This requires large radiator panels, which add mass and complexity. For a fusion-powered spacecraft generating gigawatts of thermal energy, the radiator system might need to be larger than the spacecraft itself, a vast array of heat-dissipating fins extending into the void, glowing faintly in the infrared. Those radiators must function for decades. They must not be degraded by cosmic radiation or interstellar dust. They must not be damaged by the vibration and thermal stress of a long-duration mission. Every additional system required to keep the spacecraft alive is another system that can fail, another component that adds weight, another link in a chain that stretches across decades of unsupported operation. And then there is relativity. At velocities approaching a significant fraction of the speed of light, the effects of Einstein's special relativity begin to manifest. The ship's mass effectively increases from the perspective of an external observer, meaning that more energy is required for each additional increment of speed. Time dilation occurs, with clocks on the spacecraft running slightly slower than clocks on Earth. At 10% of light speed, these effects are small but measurable. At 50%, they become significant. At 90%, they become dominant. Relativity does not prevent interstellar travel, but it ensures that the energy cost of approaching the speed of light grows without bound. There is no magic velocity threshold where the problem becomes easy. The closer you get to light speed, the harder every additional kilometer per second becomes. The universe has built a wall that grows higher as you climb it. There is one more dimension to the problem that deserves mention before we move on. Navigation. A spacecraft traveling to Proxima Centauri at a significant fraction of light speed must maintain its course with extraordinary precision over decades of flight. At 10% of light speed, the spacecraft covers roughly 30,000 kilometers every second. An error of 1/10,000th of a degree in trajectory would, over the course of a 42-year journey, result in a missed distance of hundreds of billions of kilometers. The spacecraft would sail past the Proxima Centauri system entirely, too far from the star to conduct any useful observations, too fast to turn around, too depleted of fuel to correct course. It would vanish into the interstellar void, a billion-dollar monument to the unforgiving precision that deep space demands. Navigation at these distances cannot rely on ground-based tracking stations on Earth. The round-trip signal time of nearly 9 years makes real-time course corrections impossible. The spacecraft must navigate autonomously, using onboard star trackers and inertial measurement units that maintain their calibration across decades without maintenance. The sensors must distinguish their target star from the tens of thousands of other stars visible to their instruments, and they must do so while the star field shifts due to relativistic aberration, the distortion of apparent star positions caused by the spacecraft's own velocity. At 10% of light speed, this aberration is small but measurable. At higher velocities, it becomes dramatic. The stars ahead would appear to bunch together and shift toward the blue end of the spectrum. The stars behind would spread apart and redden. The onboard navigation system must compensate for these effects in real time, or the spacecraft will lose its way in a sky that no longer looks like the sky it was programmed to recognize. Every element of the problem interlocks with every other element. Propulsion demands fuel. Fuel demands mass. Mass demands more fuel. Shielding demands mass. Navigation demands precision. Communication demands power. Power demands mass. The entire system is a web of interdependencies, each pulling the others toward failure, each resisting the efforts of engineers to make the whole thing work. The interstellar challenge is not one problem. It is 100 problems woven together, each amplifying the others, and the thread that connects them all is distance. Distance is the enemy. Distance is what makes every subsystem harder, every margin thinner, every solution more fragile. And the distance to Proxima b is 4.24 light-years, 25 trillion miles, an abyss that does not care how clever we are. Humanity has never been content to stare at boundaries. Over the past 70 years, some of the most brilliant engineers and physicists on Earth have dedicated careers, lifetimes, and reputations to the problem of interstellar propulsion. Each proposal that has emerged represents a different philosophy of attack, a different strategy for wrestling with the rocket equation, or attempting to sidestep it entirely, and each proposal, in its own distinctive way, illuminates both the staggering ingenuity of the human mind and the even more staggering indifference of the distances involved. Let us examine 5 of the most significant concepts, one at a time, giving each the attention it deserves. The first and most famous is Project Orion, the nuclear pulse propulsion concept. We have mentioned it briefly, but the full story deserves a careful telling. The idea was born in the late 1950s at General Atomics in San Diego, California, Ted Taylor, a physicist who had designed some of the most compact and efficient nuclear weapons in the American arsenal, was obsessed with the raw, untamed power of nuclear explosions. He had seen what a few kilograms of fissile material could do. He wondered what would happen if you harnessed that power not for destruction but for propulsion. He partnered with Freeman Dyson, a British-American mathematician and theoretical physicist of extraordinary range and creativity, and together they conceived one of the most audacious engineering proposals in human history. The Orion spacecraft would carry a magazine of small nuclear devices, essentially purpose-built atomic bombs, each weighing perhaps 100 kilograms. These would be ejected one at a time from the rear of the ship at intervals of a few seconds. Each bomb would detonate approximately 30 meters behind the ship. The explosion would vaporize a disk of propellant material, usually envisioned as a plastic or beryllium plate, ejected alongside the bomb, creating a pulse of superheated plasma that would slam into a massive steel and aluminum pusher plate at the base of the spacecraft. Heavy shock absorbers would smooth the individual impacts into relatively steady acceleration. The crew, insulated from the blasts by layers of shielding and damping mechanisms, would ride the ship forward on a succession of nuclear firecrackers. It sounds insane. In many ways, it was insane, but the physics worked. Small-scale tests using conventional explosives demonstrated that the pusher plate concept was viable. The pulse unit designs were grounded in well-understood nuclear weapons physics, and the projected performance was extraordinary. The most ambitious configurations of Orion, the so-called Super Orion variants, envisioned ships weighing hundreds of thousands of tons, propelled by thermonuclear devices with yields of several kilotons each, achieving exhaust velocities of 30 to 40 kilometers per second. At those exhaust velocities, and with the massive fuel supply that thousands of nuclear bombs represent, an Orion ship could theoretically reach 3 to 5% of the speed of light. At 3% of light speed, approximately 9,000 kilometers per second, the journey to Proxima Centauri would take about 140 years. Not within a single lifetime, but within a conceivable institutional timeframe. 5 or 6 generations, a cathedral-building timescale. Freeman Dyson himself imagined it as a multi-generational voyage, a floating city propelled by nuclear fire across the interstellar dark. But the obstacles were immense. The ship would need to carry thousands of nuclear weapons, each one an engineering masterpiece in its own right, stored and deployed reliably over decades. The pusher plate would endure repeated bombardment by nuclear plasma at temperatures of millions of degrees. No known material could survive that punishment indefinitely, and testing replacement plate materials would require actual nuclear detonations. The radiation environment behind the ship would be intensely lethal. The political implications of launching a spacecraft carrying thousands of nuclear devices were, even in the freewheeling nuclear climate of the late 1950s, deeply troubling. And then, in 1963, the Partial Nuclear Test Ban Treaty prohibited nuclear explosions in the atmosphere, in space, and underwater. Project Orion was officially terminated in 1965. The dream of riding nuclear fire to the stars died in a filing cabinet at General Atomics, killed not by physics, but by politics and prudence. But the dream did not stay dead entirely. In the 1970s, the British Interplanetary Society undertook a 5-year study called Project Daedalus, named after the mythological craftsman who built wings to fly. Daedalus was designed as an unmanned probe mission to Barnard's star, roughly 6 light-years from Earth. Unlike Orion, Daedalus would use nuclear fusion rather than fission. Its propulsion system envisioned inertial confinement fusion, in which tiny pellets of deuterium and helium-3 would be compressed and ignited by electron beams roughly 250 times per second, each micro-explosion pushing the ship forward. The design called for a 2-stage spacecraft, with a total initial mass of approximately 54,000 tons, of which 50,000 tons was fuel. The ship would accelerate for nearly 4 years, reaching a top speed of approximately 12% of the speed of light, then coast for the remainder of the 50-year journey. Daedalus was a landmark study. It demonstrated that interstellar flight was at least theoretically possible within the framework of known physics. But its fuel requirements were staggering: 50,000 tons of helium-3, an isotope so rare on Earth that the entire global supply amounts to a few kilograms per year. The Daedalus team proposed mining helium-3 from the atmosphere of Jupiter using giant balloon-borne extraction platforms floating in the upper clouds of the gas giant. This was, and remains, an engineering challenge so far beyond current capability that it reads more like a plot element from a science fiction novel than a mission plan. A successor study, Project Icarus, was launched in 2009 by the British Interplanetary Society and the Tau Zero Foundation to revisit and update the Daedalus concept using contemporary physics and engineering. Icarus explored alternative fusion fuels, alternative engine designs, and the possibility of deceleration at the target system. The study generated valuable research but reached the same fundamental conclusion. Fusion-powered interstellar travel is theoretically sound but demands resources and technologies that remain decades or centuries away from realization. The second approach is nuclear electric propulsion, a quieter, more patient technology. Instead of the brute violence of nuclear explosions, nuclear electric propulsion uses a compact nuclear reactor to generate electricity, which in turn powers an ion drive. Ion engines work by ionizing a propellant gas, usually xenon, and accelerating the ions to extremely high velocities using electric fields. The thrust is tiny, measured in millinewtons, less than the weight of a sheet of paper, but the exhaust velocity is very high, typically 20 to 50 kilometers per second, and the engine can operate continuously for months or years, slowly accumulating velocity in a way that chemical rockets cannot. NASA's Dawn spacecraft, launched in 2007, demonstrated the potential of ion propulsion in the inner solar system, using 3 xenon ion thrusters powered by solar arrays. Dawn visited the asteroid Vesta and the dwarf planet Ceres, achieving a total delta V of approximately 11.5 kilometers per second over its mission. That was a remarkable accomplishment, but 11.5 kilometers per second is roughly 0.004% of the speed of light. To reach even 1% of light speed, 3,000 kilometers per second, a nuclear electric spacecraft would need a delta V roughly 260 times greater than Dawn achieved. The propellant requirements, even with a highly efficient ion engine, would be enormous. The reactor would need to run continuously for decades, perhaps centuries, without maintenance, without refueling, without any possibility of repair. And even at 1% of light speed, the journey to Proxima b would still take more than 400 years. Nuclear electric propulsion is a magnificent technology for exploring the solar system. It will likely carry robotic probes to the outer planets faster and more efficiently than chemical rockets ever could. It may even enable crewed missions to Mars with transit times of weeks rather than months. But it is not an interstellar technology. The exhaust velocities, while vastly superior to chemical propulsion, remain orders of magnitude too low to cover light years in any reasonable time frame. The tyranny of the rocket equation bends slightly, but it does not break. There is an interesting variant worth mentioning here. Some researchers have proposed using a nuclear electric system not to push a traditional spacecraft, but to power a plasma magnet, a device that creates a large magnetic bubble around the ship to capture the momentum of the solar wind. The solar wind, a stream of charged particles flowing outward from the sun at roughly 400 to 800 kilometers per second, carries considerable momentum. A sufficiently large magnetic sail could theoretically ride this wind to respectable speeds without carrying any propellant at all. But the solar wind weakens rapidly with distance from the sun. By the time a spacecraft reaches the orbit of Jupiter, the wind has become too thin and too slow to provide meaningful thrust. The plasma magnet is a solar system technology, useful perhaps for rapid transit to the outer planets, but incapable of pushing a ship across light years. Beyond the heliosphere, the wind dies and the ship drifts. Another variation, the Bussard ramjet, proposed by physicist Robert Bussard in 1960, imagined scooping up interstellar hydrogen with an enormous magnetic funnel and using it as fusion fuel. The ship would never run out of fuel because it would gather fuel as it flew. In theory, a Bussard ramjet could accelerate indefinitely, approaching the speed of light over time. It is one of the most romantic concepts in interstellar mission design, Unfortunately, subsequent analysis has shown that the drag created by scooping interstellar hydrogen, which is extremely thin and must be ionized and decelerated before it can be used, exceeds the thrust produced by fusing it. The Bussard ramjet does not accelerate, it brakes. The faster it goes, the more hydrogen it scoops and the more drag it experiences. The concept, beautiful as it is, does not work. The interstellar medium is simply too sparse and too cold to serve as a fuel source for a ship moving through it. The third concept is the most radical departure from conventional rocketry. It asks a simple question with profound implications. What if the spacecraft carried no fuel at all? What if the energy came from outside the ship, beamed from a fixed installation millions of miles away? This is the philosophy behind laser sail propulsion, and it is the foundation of Breakthrough Starshot, the most ambitious interstellar mission concept currently under active development. Breakthrough Starshot was publicly announced in April of 2016 by the late physicist Stephen Hawking, the Russian-Israeli entrepreneur and investor Yuri Milner, and a board of scientific advisors that included Freeman Dyson himself, by then in his 90s. The project committed $100 million to initial research and development. The concept is elegant in its simplicity and terrifying in its requirements. Build a very small, very light spacecraft called a starship, total mass 1 to 4 grams, smaller than a postage stamp, thinner than a playing card. Pack it with miniaturized instruments, a camera, a spectrometer, a communications laser, a tiny onboard power source, all fabricated using semiconductor technology, not unlike the chips in your smartphone. Attach this starship to a light sail, a thin, reflective membrane approximately 4 meters on each side, weighing perhaps 1 gram per square meter. Then, from a ground-based or orbital laser array, fire a coherent beam of photons at the sail. The photons bounce off the reflective surface, transferring their momentum to the sail. With sufficient laser power, sustained for a sufficient duration, the starship accelerates. The target velocity is 20% of the speed of light, 60,000 kilometers per second. At that speed, the journey to Proxima Centauri takes just over 21 years. A single human career. The starship could be launched during an engineer's working life and arrive before she retires. For the first time in the history of interstellar mission design, the journey falls within the span of a single generation. But here is the problem. The laser array required to accelerate even a few grams to 20% of light speed would need to produce approximately 100 gigawatts of focused, coherent optical power. 100 gigawatts is roughly the entire installed electrical generating capacity of a moderately large nation. That power must be concentrated into a single beam, aimed with nanoradian precision at a target that is accelerating away at thousands of kilometers per second, across a distance that rapidly grows to millions of kilometers. The beam must remain focused on the sail for approximately 10 minutes, during which time the starship accelerates through 60,000 kilometers per second of velocity gain. The pointing accuracy, the beam coherence, the atmospheric compensation required to prevent the beam from scattering through Earth's atmosphere, all of these represent engineering challenges that no current technology can meet. The sail itself faces equally daunting requirements. At 100 gigawatts of incident power, the radiation pressure on the sail is enormous, but so is the thermal load. Even a sail with 99.9% reflectivity absorbs 0.1% of the beam energy as heat. 0.1% of 100 gigawatts is 100 megawatts. That is enough thermal power to melt most known materials almost instantly. The sail must be made of a material that is nearly perfectly reflective across the laser's wavelength, extremely thin, extremely light, and capable of withstanding thermal loads that would vaporize steel. No such material currently exists. Research into exotic candidates, graphene, silicon nitride, molybdenum disulfide, is ongoing but remains in the early laboratory phase. And even if every engineering challenge is solved, the result is a flyby. The starship has no fuel and no way to decelerate. It will streak through the Proxima Centauri system at 20% of the speed of light, covering the entire system in a matter of hours. During that brief window, the onboard instruments must photograph Proxima b, measure its atmospheric composition, if it has an atmosphere, detect any signs of surface water or geological activity, and transmit all of this data back to Earth across 4.24 light-years using a communications laser smaller than a grain of rice, powered by an energy source smaller than a fingernail. The data, traveling at the speed of light, would take another 4.24 years to reach us. The total mission time from launch to data reception would be roughly 25 years. The science return would be limited. A flyby gives you snapshots, not studies, moments, not seasons. The numbers are striking, not for what they promise, but for the gap between the concept and the engineering reality. Breakthrough Starshot is not a fantasy. The physics allows it, but the technology readiness level of virtually every key component, the laser array, the sail material, the ultralight instruments, the communications system, remains at the basic research stage. Decades of focused development lie ahead, perhaps generations. There is also a deeper concern with Breakthrough Starshot that is rarely discussed in popular accounts. The laser array, producing 100 gigawatts of coherent optical power, would be one of the most potent directed energy installations ever conceived. A beam capable of accelerating a gram-scale object to 20% of the speed of light could in principle be repurposed as a weapon of extraordinary destructive power. The geopolitical implications of constructing such a device are profound. No nation currently possesses anything remotely comparable. Its construction would reshape strategic calculations in ways that are difficult to predict and potentially destabilizing. This does not mean the array should not be built, but it means the project carries dimensions that extend far beyond the laboratory. It is also a question of governance, international trust, and cooperation on a scale that human institutions have rarely achieved. And there is a timing problem. Even if Breakthrough Starshot succeeds perfectly, the first data from Proxima b would not arrive on Earth until approximately 25 years after launch. If the project requires 30 years of development before the first launch, the total time from inception to data is roughly 55 years. That is within a long human lifetime, but it exceeds the duration of most research programs. Funding priorities shift, political will fluctuate, technologies become obsolete while better ones emerge. The history of large-scale scientific projects is littered with abandoned programs that ran too long and lost their institutional support before delivering results. Starshot would need to maintain momentum across more than half a century, a difficult proposition in any era. The fourth concept returns to the idea of carrying fuel, but pushes into the most exotic territory available. Antimatter-catalyzed fusion propulsion uses tiny amounts of antimatter, measured in milligrams or micrograms, to ignite deuterium-tritium or deuterium-helium-3 fusion reactions. The antimatter serves as a spark plug, concentrating enough energy in a small enough volume to trigger fusion burns that would otherwise require impractically large magnetic or inertial confinement systems. Studies at Penn State University and under the NASA Institute for Advanced Concepts explored mission architectures using antimatter-catalyzed engines that could theoretically accelerate a spacecraft to 5 to 10% of the speed of light. At 10%, the journey to Proxima b takes roughly 42 years, a human lifetime. A mission launched when a crew member is 25 would arrive when they are 67. It is the first interstellar propulsion concept that brings the journey within the biological limits of a single human life. That fact alone gives antimatter-catalyzed fusion a unique place in the literature of interstellar mission design. But the antimatter problem is inescapable. Even antimatter-catalyzed systems, which use far less antimatter than pure antimatter engines, require quantities that exceed current global production by a factor of billions. The world's particle physics laboratories have produced, in total, roughly 20 nanograms of antimatter. An antimatter-catalyzed mission might need 10 milligrams. The gap between 20 nanograms and 10 milligrams is a factor of 500,000. Closing that gap would require not just scaling up current production methods, but revolutionizing them entirely, building dedicated antimatter factories powered by energy sources that do not yet exist, operating for years or decades to accumulate a fuel supply that could fit in a thimble. And storage remains a nightmare. Antiprotons or positrons must be held in electromagnetic traps, in perfect vacuum, isolated from any contact with normal matter. Any breach in containment, any leak, any collision, and the antimatter annihilates, releasing its energy inside the spacecraft. A containment failure would not be a malfunction. It would be an explosion. The engineering tolerances required are beyond anything that spaceflight has ever demanded. There is also the question of what antimatter-catalyzed fusion would actually look like in practice. The antimatter does not simply ignite the fusion fuel like a match striking kindling. The process involves directing a beam of antiprotons into a target containing fusion fuel, where the antiproton annihilation releases enough energy in a small enough volume to compress and heat the surrounding fuel to fusion conditions. This is a miniaturized version of inertial confinement fusion, using antimatter instead of lasers as the energy driver. The timing must be precise to within nanoseconds. The antimatter delivery system must function reliably across decades of continuous operation, and the fusion reactions themselves produce high-energy neutrons that bombard the engine structure, weakening materials and inducing radioactivity over time. The engine would need periodic replacement of internal components, a maintenance requirement that is manageable for a ground-based reactor but nearly impossible for a spacecraft millions of kilometers from the nearest shipyard. The fifth approach is, in some ways, the most human. Instead of making the journey short, it proposes making the ship large. The generation ship, sometimes called a world ship, accepts that the voyage will take centuries or millennia. It does not try to outrun the problem. It tries to outlive it. Build a self-contained habitat large enough to sustain a permanent population. Equip it with closed-loop life support, recycling air, water, and waste into a perpetual cycle. Grow food in agricultural modules. Educate children in onboard schools. Launch the habitat toward Proxima Centauri at a modest velocity, perhaps 0.5% to 1% of the speed of light, and allow the journey to unfold over 400 to 1,000 years. The passengers who depart will never arrive. Their distant descendants, born and raised in a world of metal corridors and artificial sunlight, will be the ones to step onto the surface of a new world. The engineering scale is staggering. A generation ship capable of sustaining a genetically viable population, typically estimated at a minimum of several thousand individuals, would need to be enormous. Estimates range from ships several hundred meters long to ships several kilometers in length. With rotating sections to simulate gravity, redundant life support systems, hospitals, waste processing plants, manufacturing facilities to replace worn components, and entertainment and cultural spaces to maintain psychological health across generations of confinement. The total mass could easily reach millions of tons, perhaps tens of millions of tons. Accelerating even 1 million tons to 0.5% of the speed of light requires approximately 1.1 times 10 to the 25 joules. That is roughly 170 times the annual energy consumption of human civilization. For a single spacecraft, the math is striking in its brutality. The energy budget of a generation ship is not a spacecraft problem, it is a civilization problem. It requires energy resources that we do not currently possess, delivered through propulsion systems that we have not yet invented, sustained for a construction timeline that would span generations even before the ship departs. And the human challenges may be even greater than the engineering ones. What happens to a society that knows it is permanently confined? What happens to motivation when the destination is centuries away and the origin is a fading ancestral memory? Sociological studies of isolated communities, submarine crews, Antarctic research stations, long-duration space missions suggest that social cohesion degrades rapidly under conditions of confinement, monotony, and resource limitation. Depression, conflict, factionalism, cultural drift, and existential despair are well-documented responses to prolonged isolation. A generation ship is not merely an engineering project. It is a social experiment of unprecedented scope and risk, conducted with no possibility of external support, no escape route, and no margin for failure. There is a concept in population genetics called the minimum viable population, the smallest number of individuals needed to maintain genetic diversity over many generations. without succumbing to inbreeding depression, genetic drift, or the accumulation of harmful mutations. For a completely isolated population, this number is estimated at roughly 4,000 to 10,000 individuals, depending on the assumptions. A generation ship carrying fewer than this number would face a slow genetic decline, with each generation slightly less healthy, slightly less diverse, slightly more vulnerable to disease than the last. Over the course of 500 or 1,000 years, the cumulative effect could be devastating. The people who arrive at Proxima b might be a population in genetic crisis, weakened by centuries of bottleneck, poorly equipped to colonize a new world. And then there are the ethical questions that no engineering study can answer. Is it moral to consign unborn generations to a journey they did not choose? The passengers who board the ship at departure chose to go. Their grandchildren, born aboard the ship with no knowledge of Earth except through stories and recordings, did not. They are captives of a decision made before their birth, trapped in a metal world they cannot leave, traveling toward a destination they may not care about. What rights do they have? What obligations do the builders owe to the born-in-transit generations? These are not trivial philosophical puzzles. They are fundamental questions about consent, autonomy, and the ethics of multi-generational sacrifice, and they have no clear answers. Something is wrong with our assumptions, not with our physics. The physics is correct, not with our engineering. The engineering proposals are often brilliantly creative. What is wrong is the assumption that interstellar travel is a problem of the same type as the problems we have previously solved. Going to the moon was difficult, but it was a single-generation project, achievable with the technology and energy reserves of a single superpower within a decade of committed effort. Going to the stars is not a scaled-up version of going to the moon. It is a different category of challenge entirely, one that may require not a new engine or a new fuel, but a new kind of civilization. There is a sixth concept that deserves mention, though it is the most speculative of all. It does not involve propulsion in the conventional sense. It involves bending space-time itself. In 1994, the Mexican theoretical physicist Miguel Alcubierre published a paper describing a solution to Einstein's field equations of general relativity that would allow a region of space-time to travel faster than light without violating the local speed of light constraint. The Alcubierre warp drive, as it came to be known, would contract spacetime in front of the ship and expand it behind, creating a wave of spacetime that carries the ship forward while the ship itself remains stationary within its local frame of reference. The concept captured the public imagination. It seemed to offer an escape from the tyranny of distance, a genuine shortcut. But here is the problem. The Alcubierre drive, in its original formulation, requires exotic matter, a hypothetical form of matter with negative energy density. No such matter has ever been observed or produced. The energy requirements, even with refinements published by later researchers, remain staggering, potentially exceeding the mass energy of Jupiter. And there are deep theoretical objections. The interior of the warp bubble may be causally disconnected from the exterior, meaning the pilot cannot control the bubble from inside. The bubble, once created, may not be able to be stopped. The arrival of the bubble at its destination would release a catastrophic burst of accumulated radiation and blue-shifted photons, potentially sterilizing anything at the target location. And even if all of these problems were somehow resolved, we have no idea how to create or manipulate spacetime curvature on the required scale. The Alcubierre drive is not a technology. It is a mathematical curiosity, a proof that general relativity permits certain solutions, not a proof that those solutions can be physically realized. It remains, for now, in the realm of theoretical physics, not engineering. And so the landscape of interstellar propulsion stands as a graveyard of ambition. Every approach, from the crude violence of nuclear pulse to the elegant patience of ion drives, from the radical simplicity of laser sails to the exotic dreams of warp drives, eventually encounters a wall of energy, of materials, of timescales of physics. The walls are different for each approach, but they are all walls, and none has been breached. It is worth pausing here to note what all 5 practical approaches share. Each one was conceived by brilliant people. Each one is grounded in real physics, not fantasy. Each one has been studied, refined, and debated by teams of engineers and scientists with deep expertise in their fields. And each one, when subjected to the unforgiving arithmetic of the rocket equation, the inverse square law of radiation, the material properties of real substances, and the energy budgets of real civilizations, falls short. The failures are not uniform. Nuclear pulse comes closest to brute force viability, but is politically and environmentally untenable. Laser sail avoids the mass ratio problem but sacrifices deceleration and payload capacity. Fusion propulsion has the best theoretical performance, but requires technologies that may take centuries to develop. Antimatter is thermodynamically ideal, but productionally impossible. Generation ships sidestep the speed problem, but create sociological challenges without precedent. But here is the problem that connects them all. Every serious interstellar mission study eventually arrives at the same conclusion. The challenge is not finding the right engine. The challenge is that the universe is built on a scale where no single technology suffices. Interstellar travel is not an engineering problem awaiting its Wright brothers moment. It is a civilizational capacity that must be grown, slowly, across generations, through the patient accumulation of energy infrastructure, material science, institutional endurance, and collective will. There will be no eureka moment. There will be no sudden breakthrough that makes the stars accessible overnight. There will be, at best, a slow and uncertain climb toward toid capabilities that our descendants may take for granted, but that we can barely imagine. The deeper truth is this: the distance to Proxima b is not primarily a technological problem. It is an energy problem, and beneath the energy problem lies a timescale problem. And beneath the timescale problem lies something more fundamental, still a problem of identity, of what it means to be a species whose biology, psychology, institutions, and civilizational structures are calibrated to operate within a narrow window of time and space that the universe does not share and has never shared. Let us put the energy requirements into perspective with numbers that are precise enough to feel. The total annual energy consumption of human civilization, every nation, every industry, every vehicle, every light bulb, every server, every furnace on the planet, amounts to approximately 5.8 times 10 to the 20 joules per year, roughly 600 exajoules. That is an enormous amount of energy. It powers a global economy serving 8 billion people. It runs cities, farms, factories, hospitals, data centers. It is the metabolic output of an entire technological species. Now consider this. To accelerate a modest 100-ton spacecraft, roughly the mass of the International Space Station, to 10% of the speed of light, approximately 30,000 kilometers per second, would require approximately 4.5 times 10 to the 20 joules of kinetic energy. That is roughly the entire annual energy production of human civilization, compressed into a single act of acceleration, for one small spacecraft, carrying no crew, carrying no life support, carrying no deceleration fuel, just a bare stripped-down probe, hurled outward at a speed that would still take 42 years to reach Proxima b. Let that sink in. If that same probe needs to decelerate at the other end, double the energy. If the mission requires a crewed habitat instead of a bare probe, a ship weighing thousands of tons instead of 100, multiply the energy by a factor of 10, or 100, or 1,000. If the mission requires a colony ship capable of sustaining a viable population, multiply again. The energy requirements scale linearly with mass and quadratically with velocity. Every increase in ambition, every step from a flyby probe to a crewed ship to a colony vessel, pushes the energy requirement further and further beyond the productive capacity of our entire civilization. This is not science fiction. This is thermodynamics. This is the conservation of energy, applied not to a laboratory experiment, but to the grandest ambition our species has ever entertained. Energy cannot be created from nothing. It can only be converted from one form to another. And converting enough energy to push meaningful mass across 4.24 light-years requires either consuming energy reserves on a planetary scale or tapping energy sources that we have not yet begun to harness. In 1964, the Soviet astronomer Nikolai Kardashev proposed a framework for classifying civilizations by their energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the 16 watts. A Type 2 civilization harnesses the full energy output of its host star, approximately 10 to the 26 watts. A Type 3 civilization controls the energy of an entire galaxy, roughly 10 to the 36 watts. By this metric, humanity is currently a Type 0.73 civilization. We do not yet fully exploit even the energy resources of our own world. We are roughly 200 years from reaching Type 1 by most optimistic projections. And interstellar travel, real interstellar travel, not flyby probes but missions that carry people and cargo and possibility, is arguably a Type 2 capability. It requires energy on the scale of a star's output. We are trying to cross an ocean in a rowboat, and we have not yet finished building the dock. To make this mismatch visceral, consider a simple comparison. The energy required to accelerate a single kilogram of matter to 10% of the speed of light is approximately 4.5 times 10 to the 14 joules. That is 450 terajoules. For 1 kilogram, that is roughly the energy released by 100,000 tons of TNT, approximately 6 times the yield of the nuclear bomb dropped on Hiroshima, to accelerate a single kilogram. Now imagine accelerating a spacecraft weighing 10 tons. That requires the energy of 60,000 Hiroshima bombs. A 100-ton spacecraft? 600,000 Hiroshima bombs. A generation ship weighing 1,000,000 tons? 6 billion Hiroshima bombs. The numbers do not merely grow, they explode, they detonate into absurdity. And at every scale, the energy must be produced, stored, converted into thrust, and delivered with precision over months or years of continuous acceleration. There is no shortcut. There is no clever trick that makes the energy go away. It must be paid, in full, in advance, with no refunds. Here is another lens on the same mismatch. The sun outputs approximately 3.8 times 10 to the 26 watts. Every second, the sun releases more energy than human civilization has consumed in its entire history. If we could capture even a vanishingly so small fraction of the sun's output, say 1/10 billionth, we would command 10 to the 16 watts, roughly equal to the total power consumption of modern civilization. With that power, dedicated entirely to interstellar propulsion, we could launch a modest probe to Proxima Centauri perhaps once a decade. But capturing 1/10 billionth of the sun's output would require a solar collector with an area of several thousand square kilometers, orbiting close enough to the sun to intercept a concentrated beam of radiation, operating in temperatures that would challenge the most heat-resistant materials known to engineering. This is the concept of a Dyson swarm, first described by Freeman Dyson in 1960, a cloud of orbiting solar collectors gradually encircling a star. It is a magnificent idea. It is also a project that would take centuries or millennia to construct, even with technology far more advanced than what we currently possess. The timescale problem is equally sobering. Consider the 1,000-year journey embedded in the title of this documentary. 1,000 years. If a spacecraft had been launched from Earth 1,000 years ago, in approximately the year 1026, it would have departed during the late Viking Age. William the Conqueror had not yet been born. The Domesday Book had not been written. The Magna Carta was 2 centuries in the future. The printing press was 4 centuries away. The concept of the nation-state did not exist. The institutions that funded and operated the mission would have long since dissolved. Their languages evolved into unrecognizable forms, their borders redrawn 100 times, their very cultures absorbed into successor civilizations that the original mission planners could not have imagined. Now imagine launching a spacecraft on such a journey today. Who maintains the mission over a millennium? Who monitors the spacecraft? Who receives the data when it finally arrives? The institutions that exist today, the governments, the space agencies, the universities, are unlikely to persist in recognizable form for 1,000 years. No human institution ever has. The Catholic Church, often cited as the longest surviving institution in Western history, has transformed so profoundly over its 2,000-year existence that a 6th-century bishop transported to the modern Vatican would recognize almost nothing about its theology, governance, or practice. Governments rise and collapse. Empires dissolve. Languages drift. Technologies are forgotten and rediscovered. The continuity required for a 1,000-year mission is not merely difficult to achieve. It is without precedent in the entire history of human civilization. Let that sink in. The psychological dimension deserves its own weight. Human beings are not built for patience on these scales. Our planning horizons extend, at their most ambitious, a few decades into the future. Corporations plan in fiscal quarters. Governments plan in election cycles. Even the most visionary infrastructure projects, the medieval cathedrals that took generations to complete, offered visible progress to each generation of builders. A stone arch completed here, a flying buttress raised there. Each generation could see the cathedral growing. Each generation could take pride in its contribution and anticipate the contributions of the next. An interstellar mission offers nothing comparable. No generation of mission controllers will see the spacecraft arrive. No taxpayer will benefit from the data returned. No scientist who designs the instruments will live to see them activated. The motivation to sustain such a project across wars, economic depressions, pandemics, political revolutions, technological disruptions, and shifts in cultural values is unlike any challenge our species has ever confronted. It requires a form of intergenerational commitment that has no historical model and no guarantee of success. Consider a concrete analogy. The Gothic cathedrals of medieval Europe are often cited as examples of multi-generational projects. Notre Dame de Paris took roughly 182 years to complete, from 1163 to 1345. Cologne Cathedral took more than 600 years, from 1248 to 1880. These projects spanned generations, and each generation contributed labor and resources to a structure it would never see finished. But there is a crucial difference between building a cathedral and launching an interstellar mission. The cathedral was always visible. Every worker could see the walls rising. Every generation could walk through the nave, touch the stone, feel the space growing around them. The cathedral offered tangible, sensory feedback at every stage. An interstellar mission offers nothing. For decades after launch, perhaps for centuries, the spacecraft would be an invisible dot, invisible even to the most powerful telescopes, drifting silently through a void from which no signal can return in any reasonable time frame. There is no wall to touch, no nave to walk through, only faith in a trajectory calculated by people long dead, faith that the laws of physics have not changed, faith that the mission remains worth completing. What kind of society sustains that faith? What kind of institutions carry that purpose across centuries of change? We do not know, because no such institutions have ever existed. The longest-running continuous organizations in human history are religious orders and a handful of universities, and even they have undergone transformations so profound that their founding members would scarcely recognize them. A mission to Proxima Centauri would outlast all of them. It would require something new, something without precedent, a form of social organization calibrated to timescales that dwarf anything our species has ever attempted. There is a concept in environmental philosophy called the seventh generation principle, attributed to the Haudenosaunee Confederacy. It holds that decisions should be made with consideration for their impact 7 generations into the future, roughly 140 to 175 years. This principle is sometimes held up as a model for long-term thinking. But interstellar travel demands not 7-generation thinking, but 40-generation thinking, or 400-generation thinking. The principle does not merely need to be extended, it needs to be transformed into something our psychological architecture may not support. Consider a thought experiment that places our situation in temporal perspective. Imagine compressing the entire history of the universe, from the Big Bang to the present day, into a single calendar year of 365 days. The Big Bang occurs at midnight on January 1st. The first stars and galaxies form around January 15th. The Milky Way assembles sometime around March. Our Sun and Solar System form around September 1st. The first single-celled life appears on Earth around September 25th. Multicellular organisms do not emerge until November. Dinosaurs appear on December 25th. They go extinct on December 26th. The entire history of Homo sapiens, all 300,000 years of it, fits into the last 14 minutes of December 31st. all of recorded human civilization, writing, agriculture, mathematics, philosophy, science, all of it occupies the last 26 seconds. The Industrial Revolution begins in the last 1.5 seconds. The space age begins in the final quarter second. In this compressed cosmic calendar, the 1,000-year journey to Proxima b would last about 0.00023 seconds. A flicker, a shutter click, and yet that flicker, that cosmically imperceptible instant, is longer than any project our species has ever sustained. We are creatures of the last heartbeat of cosmic time, attempting a feat that the universe measures in nanoseconds, and finding that our institutional endurance, our social cohesion, our very biological patience is insufficient for the task. And yet the universe remains indifferent to our limitations. The distance does not shrink because we find it inconvenient. The speed of light does not increase because we wish it would. The energy requirements do not soften because we have done impressive things before. These are not obstacles placed in our path by a hostile cosmos. They are the geometry of existence. The universe was not designed for travelers. It was built, if it was built at all, on scales so vast that even photons, the fastest objects in nature, take years to traverse the gaps between neighboring stars and billions of years to cross the observable cosmos. There is a thought experiment that helps convey this isolation. Imagine you are standing on a beach, looking out at the ocean. You can see the horizon, roughly 3 miles away, on a clear day. Now imagine that the ocean has no ships, no planes, no satellites, no cables running along the bottom. Just water, stretching endlessly in every direction. And somewhere, far beyond the horizon, there is another beach. Another person standing on it. You can see a faint light from their campfire at night, flickering at the very edge of perception. You know they are there, but you have no boat, no raft, no swimmer's endurance sufficient to cross. You have only the shore beneath your feet and the knowledge that the other shore exists. That is what interstellar space feels like, translated into human experience. We see the fires of other stars. We know the shores are there, but the ocean between is wider than anything our species has ever crossed. And we have not yet learned to build the ship. This metaphor extends further. Even if you could build a boat capable of crossing that ocean, the crossing itself would change you. A journey of centuries would not produce the same civilization at the destination that departed from the origin. The passengers, their descendants, their culture, their language, their values, would all evolve during the transit. A generation ship that left Earth carrying 21st century humans would arrive carrying something different. Not necessarily better or worse, but different. Changed by centuries of isolation, of enclosure, of living without a sky, without seasons, without the smell of rain or the sound of wind in trees. The journey is not merely a physical crossing, it is a transformation, and the beings who arrive may have as little in common with the beings who departed as we have with our ancestors of 1,000 years past. This is the deeper truth. The stars are not merely far away in distance, they are far away in capability, in energy, in institutional endurance, in civilizational maturity. Reaching Proxima b is not an engineering problem to be solved by a clever team in a decade of focused work. It is a civilizational transformation, a shift in the fundamental nature of what humanity is and what humanity can sustain. And that transformation, if it comes, will not arrive quickly. It will arrive, if at all, on a timescale measured not in years or decades, but in centuries or millennia. We must become something we have never been before we can go somewhere we have never gone. Perhaps the most unsettling aspect of this realization is how it reframes the question of intelligence in the universe. We tend to assume that any sufficiently advanced civilization would eventually develop interstellar travel, that it is a natural milestone on the path of technological progress, like fire, agriculture, writing, and electricity. But what if it is not? What if the energy and timescale barriers we have described are universal? What if every intelligent species that arises on every habitable world in the galaxy encounters the same ruthless arithmetic? What if the distance between stars is not merely an engineering challenge for us, but a fundamental constraint on all life, everywhere? In that case, the galaxy might be full of technological civilizations, each trapped in its own star system, each gazing outward at the same unreachable lights, each arriving at the same devastating conclusion. The universe would be alive, but quarantined. Every species an island, every star a prison with a view. And if that is the architecture of the cosmos, if isolation is not an accident but a feature, then what does that tell us about the nature of the universe itself? Some physicists have speculated that the vast distances between stars may serve a kind of protective function. A universe in which interstellar travel were easy would be a universe in which aggressive civilizations could expand without limit, consuming resources, displacing other species, and potentially sterilizing entire regions of the galaxy. The difficulty of interstellar travel may be, in some deep sense, a safety mechanism, a firewall between civilizations, a guarantee that no single species can dominate the galaxy because the energy cost of doing so is simply too high. This is, of course, speculative. It may be nothing more than a comforting narrative imposed on an indifferent cosmos, but it is a thought worth holding, if only because it transforms the loneliness of our situation into something slightly less bleak. We are not trapped because the universe is cruel. We are separated because the universe is perhaps wise. Whether that wisdom is real or imagined, the practical result is the same. We are here. Proxima b is there. And the distance between us is, for now and for the foreseeable future, a distance we cannot cross. So what does all of this mean for us? What does it mean for our species? Perched on this small, damp, sunlit world, gazing outward at a sky, crowded with stars we may never touch, orbiting a galaxy we may never cross. The first implication is humility. Deep, structural, unyielding humility. We live in an age of extraordinary technological confidence, and for good reason. In the span of a single century, humanity went from the Wright brothers' first powered flight at Kitty Hawk in 1903, a 12-second, 120-foot hop across a windy North Carolina beach, to the International Space Station, a 420-ton habitable laboratory orbiting Earth at 28,000 kilometers per hour, staffed continuously by rotating crews of astronauts since November of 2000. We split the atom. We walked on the moon 6 times. We decoded the human genome. We built machines that can beat the best human players at chess, Go, and Jeopardy. The trajectory of technological progress has been so steep, so relentless, so apparently unstoppable that it is easy to assume every barrier will eventually yield. Every distance will eventually be crossed. Every problem will eventually be solved. But the interstellar barrier is different in kind from every barrier humanity has previously overcome. The Atlantic Ocean is roughly 3,000 miles wide. Humans crossed it in wooden ships, powered by wind and muscle. The distance to the moon is 238,000 miles. Humans crossed it in 3 days using chemical rockets. The distance to Proxima b is 25 trillion miles. The increase in scale from the moon to Proxima b is not incremental. It is not a step up a staircase. It is a leap from the bottom of a staircase to the roof of a skyscraper. The physics is not merely harder. It is categorically different. It requires energies we cannot produce, timescales we cannot sustain, and materials we cannot fabricate. The history of human exploration is a story of barriers falling. The interstellar barrier has not fallen. It has not even budged. This does not mean the journey is permanently impossible. It means the journey requires a different kind of civilization than the one we currently inhabit. A civilization that generates energy on stellar scales. A civilization that builds institutions capable of enduring for millennia. A civilization that can commit resources to projects whose returns lie far beyond the lifetimes of anyone involved in the planning. A civilization, in short, that has grown up, that has matured beyond quarterly reports and election cycles and 5-year plans. And we have not yet grown up. We are an adolescent species, powerful but short-sighted, brilliant but impatient, capable of extraordinary feats, but unable to sustain attention across the timescales that interstellar travel demands. The second implication concerns our understanding of cosmic solitude. If the stars are as inaccessible as the physics suggests, then each star system is, in a profound and practical sense, an island, not merely a distant place, but a separate world, cut off from every other world by gulfs of space and time that make meaningful interaction extraordinarily difficult. The light from Alpha Centauri that reaches your eyes tonight departed that star 4 years and 4 months ago. The light from Sirius left 8.6 years ago. The light from Betelgeuse has been travelling for roughly 700 years. When you look at the night sky, you are not seeing the universe as it is now. You are seeing the universe as it was. Each star is a window into a different moment of cosmic history. If another intelligent civilization exists around Proxima Centauri, and if they are broadcasting electromagnetic signals at this very moment, those signals will not reach Earth for 4.24 years. Our reply would take another 4.24 years. A single exchange of greetings would require nearly a decade. A sustained dialogue, the kind of conversation that might lead to mutual understanding, cultural exchange, or collaborative science, would require centuries, if not millennia. Two civilizations separated by 4 light years are not neighbors in any meaningful sense. They are correspondents, exchanging messages that take years to deliver, unable to share a meal, a handshake, or even a live conversation. And if this is true for the nearest star, the closest possible neighbor, it is exponentially more true for the broader galaxy. The Milky Way stretches 100,000 light-years from edge to edge. A signal sent from one arm of the galaxy to the opposite arm would take 100,000 years to arrive. Civilizations on opposite sides of the galaxy could rise, flourish, stagnate, and collapse to dust without ever knowing of each other's existence. The universe may be teeming with intelligent life, but the distances may ensure that none of those lives ever meet, ever communicate, ever confirm that they are not alone. This is perhaps the most quietly devastating resolution to the Fermi paradox, the question of why, if the galaxy is so large and so old, we have never detected evidence of another technological civilization. Perhaps they are out there. Perhaps they have always been out there. And perhaps the universe is simply too big and too slow for any of them to find each other. The physicist Enrico Fermi asked his famous question, "Where is everybody?" over lunch at Los Alamos National Laboratory in 1950. The question seemed almost casual. The galaxy is roughly 13 billion years old. There are hundreds of billions of stars. Even if intelligent life is rare, even if only 1 in a million star systems produces a technological civilization, there should be hundreds of thousands of them in the Milky Way alone. Some of them should be millions of years older than us. Some should have had ample time to colonize the entire galaxy. And yet, when we look outward, we see no evidence of their existence. No megastructures, no signals, no artifacts, nothing. Just silence and starlight. The distance argument offers a chilling explanation. Perhaps civilizations do arise frequently. Perhaps some of them are millions of years more advanced than our own. But perhaps none of them, no matter how advanced, has found a way to cross the interstellar void efficiently. Perhaps the speed of light is not merely fast but absolute, a cosmic speed limit that no technology can exceed or meaningfully approach without expenditures of energy that exceed the capacity of any civilization. In that case, the galaxy would be a vast archipelago of inhabited islands, each aware of the other's existence through their starlight, none able to visit, none able to meaningfully interact. The silence would not be a mystery, it would be a consequence of geometry. The answer to Fermi's question would not be that they are not there, it would be that they are there, and they are just as trapped as we are. This possibility carries a strange emotional weight. On one hand, it implies that we are not alone in the universe, that consciousness, curiosity, and technological capability may have arisen on countless worlds, scattered across the galaxy like seeds in a vast and silent garden. On the other hand, it implies that none of those seeds will ever meet, that the garden is too vast, the spaces between their flowers too wide, for any cross-pollination to occur. The universe may be a library full of books, each written in a language only its author speaks, each sealed behind glass that no hand can break. The knowledge exists, the voices exist, but the conversation never begins. The third implication is the most personal and the most difficult. If humanity cannot leave this solar system, or cannot leave it for thousands of years, then the long-term fate of our species is bound to the fate of our star. The Sun is currently about 4.6 billion years old. It has perhaps 5 billion years of hydrogen fusion remaining before it exhausts its core fuel supply and begins to swell into a red giant expanding to roughly 100 times its current diameter and engulfing the orbits of Mercury and Venus. Long before that, perhaps within 1 billion years, the Sun's gradually increasing luminosity will have raised Earth's surface temperature enough to boil away the oceans and render the planet uninhabitable for any form of life as we understand it. 1 billion years is an enormous span, but it is not infinite, it is a deadline. And the question of whether we can reach the stars, whether we can send seeds of life and consciousness to other worlds before our own world becomes uninhabitable, is not an abstract philosophical musing. It is the most concrete, the most consequential question our species will ever face. It is the question of whether the 4 billion years of biological evolution that produced sentience, language, music, mathematics, and love will mean something beyond this one small planet, or whether it was all a brief accident, a flicker of complexity in the thermal decay of an ordinary star. There is a philosophical concept sometimes called the cosmic perspective. It is the experience of seeing Earth and human civilization from the outside, from a vantage point so distant that borders dissolve, conflicts shrink to insignificance, and the fragility of everything we have built becomes painfully apparent. The astronauts who have experienced this firsthand looking back at Earth from orbit or from the surface of the Moon have described it as overwhelming. The Earth appears small, beautiful, impossibly delicate, a blue marble suspended in an ocean of black, and the knowledge that everything, every life, every story, every song, every war, every love, every regret, is happening on that one small sphere produces a feeling that many of them described as both terrifying and sacred. The interstellar distance problem deepens that feeling immeasurably, because it is one thing to see Earth as small and fragile. It is another to understand that Earth is also isolated, marooned, separated from every other potentially habitable world by distances that may never be crossed. We are not merely small. We are alone in a practical sense that no amount of philosophical generosity can soften. Other worlds may exist, other minds may think, but the space between us and them is so vast, so utterly unforgiving, that we may be permanently confined to our one small corner of the galaxy, peering out at a universe we can see but cannot visit. And yet there is something redemptive in the recognition, because if we are alone, if we are trapped, if the stars are truly beyond our reach for the foreseeable future, then this world, this one world, becomes infinitely precious. Every species that lives here, every ecosystem that functions, every river that flows, every breath of atmosphere that shields us from the vacuum becomes irreplaceable in a way that is difficult to fully absorb. There is no backup planet. There is no second chance waiting at Proxima b. There is only here, only now. Only this fragile, improbable, astonishingly beautiful world carrying its cargo of life through the darkness at 67,000 miles per hour, orbiting a star that will not burn forever. That knowledge should not paralyze us. It should focus us. It should clarify what matters and what does not. It should remind us that the greatest journey we may ever take is not to Proxima b, but toward a deeper understanding of the home we already have, and a fiercer determination to protect it. The stars can wait. The Earth cannot. We began tonight with a number, 4.24 light-years, the shortest distance between our Sun and another star, the smallest gap in the vast, mostly empty lattice of the Milky Way galaxy, a distance so modest by the standards of the cosmos that it barely registers as a pixel on a map of the galaxy. And yet, when we have spent these hours translating that number from the clean, comfortable abstractions of astronomy into the hard, unyielding realities of physics, engineering, energy, and human biology, it has become something else entirely. It has become a wall. Not a wall of stone or steel or any material that human hands could breach. A wall of exponential mathematics, of energy budgets that exceed the output of civilizations, of journey times that exceed the endurance of institutions, of timescales that make human history look like a footnote in a book no one will read. Proxima b is there. It is real. It orbits its dim red star in the southern sky, a world roughly the mass of Earth, bathed in the ruddy light of a star 1/8 the mass of our Sun. It may have oceans, it may have clouds, it may harbour chemistry complex enough to hint at biology, or it may be a barren, radiation-scorched wasteland, stripped of atmosphere by the violent flares of its host star. We do not know, And the quiet, persistent tragedy of our moment in cosmic history is that we cannot go and find out. Not because we lack curiosity, which we have in abundance. Not because we lack courage, which our species has demonstrated repeatedly. But because the universe placed the stars too far apart for creatures who live a century and burn chemical fuel and build institutions that rarely outlast a millennium. 25 trillion miles. If you began walking today at 3 miles per hour, without ever pausing, you would arrive at Proxima b in approximately 950 billion years. That is more than 65 times the current age of the universe. At the speed of the fastest car ever built, the journey would take over 27 million years. At the speed of the fastest jet ever flown, the Lockheed SR-71 Blackbird, at roughly 2,200 miles per hour, the journey would take 1.3 million years. At the speed of Voyager 1, 38,000 miles per hour, the journey would take over 70,000 years. At 1% of the speed of light, faster than any human-made object has ever travelled, the journey would require 424 years. At 10% of light speed, a velocity that would demand the energy output of an entire civilization, 42 years. 42 years. One adult lifetime. That is the floor. The absolute minimum, achievable only with physics we have not yet mastered, materials we have not yet fabricated, energy sources we have not yet tapped, and engineering tolerances we have not yet approached. And even in that best case, the travellers would arrive as elderly veterans of a journey that consumed the richest years of their lives, setting foot on a world that might offer nothing but silence and stone. Perhaps it will not always be this way. Perhaps some future civilization, centuries or millennia downstream from ours, will crack open the energy problem and build the engines we can only sketch on whiteboards. Perhaps they will learn to harness the full output of the sun, wrapping it in a constellation of collectors, powering laser arrays that push flotillas of light sails toward the stars at meaningful fractions of light speed. Perhaps they will engineer bodies that do not age, minds that can endure centuries of solitude, societies that can sustain purpose across time spans that would swallow our current institutions whole. Perhaps they will discover physics we have not yet glimpsed, hidden dimensions, shortcuts through the geometry of spacetime, ways to fold the distance or step outside it entirely. Or perhaps they will not. Perhaps the stars will remain what they have always been for our species, beautiful, unreachable lights. Perhaps the silent distances between suns are not challenges to be overcome, but boundaries to be respected. Perhaps the universe's final answer to our grandest question will be the same answer it has always given. Silence, distance, the patient, unyielding indifference of empty space stretching in every direction, forever. There is a strange comfort in that possibility, if you let it settle long enough, because it means that this moment matters. This world matters. This fragile, accidental, astonishing planet, spinning in its narrow habitable zone around its ordinary yellow star, matters more than any distant world we might one day reach. If the stars are beyond us, then what we have here is everything. Not a stepping stone, not a launch pad. Everything. The only garden in a desert that stretches forever in every direction. The only fire in an infinite night. We are a young species. We have been technological for barely a century. We have been spacefaring for barely 60 years. The universe has been expanding for 13.8 billion years. Perhaps we are simply too early. Perhaps we are the first draft, the rough sketch, the prototype species that comes before the one that finally cracks the code. Perhaps 1,000 years from now, or 10,000, or 100,000, our descendants will look back at this moment and smile at how close we were to understanding and how far we still had to go. But even if that is so, even if we never reach Proxima b, even if no human hand ever touches the soil of another world, orbiting another star, the asking matters, the reaching matters. The fact that a species of improbable, upright, short-lived primates, standing on a thin crust of rock and water, orbiting an unremarkable yellow star in the unfashionable suburbs of an ordinary spiral galaxy, looked up at the night sky and whispered, "How far is it? And how do we get there?" That fact is itself extraordinary. It is the cosmos waking up. It is matter measuring the distance between matter. It is the universe, through us, becoming aware of its own terrifying, magnificent, indifferent scale. We are temporary. We know this. Every one of us lives for a handful of decades, and then returns to the dust and the elements from which we were briefly assembled. We are patterns in matter and energy, complex enough to understand our own impermanence, brief enough to feel the sting of it, and perhaps the greatest expression of that brief complexity is the desire to reach beyond ourselves, to send something, anything, a signal, a probe, a hope, across the unimaginable distances that separate the islands of light in this dark universe. It may not work, it may never work, but the attempt, the calculation, the dream, these are themselves a form of arrival. We arrive at understanding even if we never arrive at the destination. Consider this. Proxima b has been there for billions of years. It was there before life on Earth emerged from the oceans. It was there before the first fish grew legs and crawled onto land. It was there before the dinosaurs rose and fell. It was there before the first hominid stood upright on the African savanna and looked up at the stars. It will be there long after we are gone, long after our sun has swollen and dimmed and cooled to a white ember drifting through the galaxy's slow rotation. Whatever happens to us, Proxima b will continue its 11-day orbit around its red dwarf star, bathed in ruddy light, indifferent to whether it is observed or visited or forgotten. And we, in our brief moment of awareness, have found it. We have detected its wobble. We have measured its mass. We have calculated its orbit. We have wondered whether it has oceans. We have dreamed about sending ships. That knowledge, imperfect and incomplete as it is itself a kind of bridge across the void. Not a physical bridge, not a bridge that carries passengers, but a bridge of awareness, a bridge of knowing. The distance remains, the silence remains, but the knowing is new, the knowing is ours. Tonight, that distance is 4.24 light years, 25.2 trillion miles, 1,000 years, or 70,000 years, or perhaps forever. We do not yet know. All we can do is keep looking up, keep calculating, keep dreaming of velocities our engines cannot yet reach and energies our civilization cannot yet command. The stars are patient. They burn on timescales that make our entire existence a passing shadow. They will wait for us, if we ever come. And if we never come, they will wait still, burning on, keeping their worlds and their secrets and their silence, long after the last human eye has closed and the last human question has faded into the dark.